Well, hi everyone. My name is Ollie Shortall from the Department of Earth Sciences and Institute of Astronomy, and it's my pleasure to welcome you all here today for this special out-of-term seminar on the recent detection of phosphine in Venus's atmosphere. It's just been over a week now since the Greaves et al. Result was published in Nature Astronomy, and an ensuing flurry of interest in the potentially biological origin of the phosphine detected in Venus's atmosphere. A key piece of the puzzle for interpreting this observation is the atmospheric chemistry of phosphine, what its lifetime is in Venus's atmosphere, and therefore what level of production would be required to sustain it at its reported 20 ppb level. And of course, whether that level of production is uniquely achievable by life, or whether there potentially are other sources, which I'm sure people are wildly speculating on as we speak now. We're very fortunate to have one of the authors of this study with us in Cambridge, Dr. Paul Rimmer, who's an expert on the photochemistry in Venus's atmosphere and can speak to us on this kind of central part of the story of this paper, which is really exciting. So thank you, Paul. To give a little background, Paul is a Simons postdoctoral fellow at the University of Cambridge, working between the Department of Earth Sciences, Cavendish Astrophysics, and the LMB on a whole range of interesting projects. In addition to Venus, Paul is working on Earth's early atmosphere, exoplanetary atmospheres, and a range of questions to do with the origin of life and the conditions required for life's origin. But today, we're very excited to have Paul speaking to us about this exciting result and the phosphine photochemistry in the clouds of Venus. So Paul, hand it over to you. Oh, and just one final logistical point, we'll take questions at the end, and you can put those in chat. I can pitch them at the end. Thanks.
All right. Thank you very much, Ollie, for setting this up, and thanks to everyone for showing up to hear about phosphine photochemistry in the clouds of Venus. So we'll first start by talking about the changing face of Venus. There are these historical visions of Venus. This is from a slide that I got thanks to David Grinspoon. This is especially relevant for a Cambridge talk because this particular article from the New York Times in 1928 mentions Arthur Eddington and his speculation that Venus is probably very, very temperate, very, very comfortable on the surface, and could be teeming with life. Isaac Asimov and many other science fiction writers wrote about the possibilities of all sorts of different kinds of life on the surface of Venus. And this was all based on what we could see at the time. This might be a sort of warning for future exoplanet science, that appearances can sometimes be deceiving, because once a probe was actually sent there, the New York Times titled this "Venus Says No." And it's referring to Venus pretty much saying no to life. The surface of Venus is hot enough to melt lead, and in fact did so with one of the particular landers. This is a slide that I also ended up taking from David Grinspoon, who has a story about one of the Russian landers carrying a bust of Vladimir Lenin with it, and now there is a small lead pool somewhere on the surface of Venus where that bust once was. But even though Venus says no to the surface, it didn't say a definitive no to the clouds, at least in the mind of one particular astronomer and one prebiotic chemist. Carl Sagan and Harold Morowitz looked into the possibility of there being life in the clouds of Venus in 1967. Let me just see if I can minimize, because right now all of your faces are covering a part of the slides. I'm pretty sure that I'll remember most of what's on that particular corner, but if I do get into trouble, I'll let you know. So life in the clouds of Venus, the basic argument for this is that when you get to about roughly 1 bar, you are actually at about room temperature, roughly, somewhere around 20 degrees. You could have droplets. The droplets themselves, as we know now, are made of sulfuric acid, which definitely poses a problem. But at least in terms of temperature and in terms of there being some sort of solvent, the best place to look for life on Venus would be the clouds. And many different researchers have followed this up. Principally among them, David Grinspoon, who's written quite a bit about the possibility of life on Venus and various different sorts of observations that may or may not be able to be explained in that way, has a very, very nice book about the clouds of Venus, which is mentioned there, if you're interested further in that. Well, it does turn out that the Vega balloon probe, which gave us a sort of early picture of the constitution of Venus's atmosphere, measured phosphorus. So we have speculations about life on Venus. We have more than just speculation about phosphorus on Venus. This is a Vega balloon probe on display. It looks the same as the probe that went into the atmosphere. And it made several measurements of Venus's atmosphere. It measured all sorts of different things. And there's a list of papers that you can look up published in the 70s, 80s, and then some return to that data in the late 90s. It observed that phosphorus is at about the same abundance as sulfur. So there's an incredible amount of phosphorus, if this measurement is correct, in the atmosphere of Venus. It's incredibly phosphorus rich, and it's incredibly sulfur rich. There's a little bit of a warning about this. This probe also predicted that the lower atmospheric SO2 drops to about 1 part per million. This is inconsistent with recent remote observations. The Mark et al. Paper from 2008 was able to look through an atmospheric window and get an idea about what the SO2 is deeper within Venus's atmosphere, around 35 kilometers. And it doesn't appear to drop off the same way that the probe did. So this is a sort of warning about taking these particular measurements of abundances as gospel. The next question, though, is what is the phosphorus actually made of, which Vega didn't answer at all. So even if you accept that there's just tons of phosphorus in Venus's atmosphere, Vega doesn't say how the phosphorus is speciated. And one way to look at this is phosphorus oxidation. And we'll start by looking at phosphorus oxidation in another place where phosphorus, and in fact phosphine, has been observed, which would be Jupiter. And there's a nice paper by Shannon Vischer published in 2006 about this. It turns out that deep within Jupiter's atmosphere, phosphine is the thermochemically preferred form of phosphorus. And as you rise up into the atmosphere, you get this phosphorus trioxide. It's this sort of cage-looking kind of molecular structure. Although it turns out that the amount that you get and the turnover of this doesn't match in Jupiter's atmosphere, because it turns out that you need temperatures higher than what you have when this shift happens. And so the atmosphere is quenched to prefer phosphine. On Venus, interestingly enough, in the deep atmosphere, you end up forming this P4O6, and higher up in the atmosphere, you expect phosphoric acid. So on Venus's atmosphere, on Earth's atmosphere, you would really expect very, very little phosphine, just undetectable quantities. It does turn out that there is some phosphine which is observed on Earth, and it is considered to be a sign of life on Earth. It's produced by industrial processes, but as Glindemann has studied in many papers, including this 1996 paper, it's produced by anoxic microbes. Clara Souza Silva has followed this up and done an incredible amount of work better elucidating the potential for phosphine production, not just on Earth, but on other planets. And that appears in a 2020 paper about phosphine on exoplanets. So then we move on, and recently Jane Greaves and co-authors, including myself, published this, this detection of this 1 millimeter feature in the clouds of Venus, observed via the James Clerk Maxwell telescope and ALMA. The feature is unlikely to be an artifact, and we compared it to a lot of different possible molecules, as I will get into. I'm going to encourage people at the end who are interested in submillimeter astronomy, microwave astronomy, to please ask lots of questions. I probably won't be able to answer them because I'm not an observer, but Jane Greaves will be speaking on this sometime in the next few weeks, and I can relay your questions to her so that she can make sure to address them well during her own talk. So there's this 1 millimeter feature, or this feature close to 1 millimeter. We considered a whole bunch of candidates, specifically Clara Souza Silva and Hideo Sagawa considered a whole bunch of different candidates. A lot of them don't have anything in this particular region. The ones that do, some of them aren't even listed here, but they're things like particular isotopes of glycine and things. And the two best candidates that wouldn't be even more extraordinary than phosphine itself in Venus's atmosphere is a particular transition of SO2 and phosphine itself. Both of these were modeled to see how well they explain the feature. And the red line is the phosphine and the green line is the SO2. You can see that the SO2, the sulfur dioxide, is a little off center, and it's not nearly deep enough to explain this particular feature, meaning that either we're very wrong about SO2 spectroscopy, or this really can't be sulfur dioxide. This, of course, does not rule out that it could be something unknown, something that we just haven't measured in this particular region. But I'm going to set that aside for now. This result generated a lot of news, various things. For the news stories, I especially recommend the National Geographic, which gave a very nice balanced story of this that actually discussed both the observations and the implications of those observations. It also generated tweets from various celebrities and Nobel laureates, one of whom would be known here. And then it also got its own XKCD comic, which actually encapsulates a lot of what I'll be talking about in the rest of the talk. I'll give you a moment to read that if you haven't. So I'm going to draw your attention to the center panel that says these molecules might be produced by life or by weird high heat chemistry. So this is already proposing a possible explanation right there. And we've gotten a lot of tweets and a lot of emails proposing possible explanations. And so I thought that it would be useful to structure the talk around what the photochemistry actually tells us about the phosphine, as a way of, if you have ideas, anyone here for this talk has ideas about how phosphine could be in the atmosphere of Venus, here's what you need to do. Here's the test that you need to pass. I'm not sure exactly why that happened. Let's see, there. What do you need to do to explain the 20 parts per billion phosphine in the clouds of Venus? And so just to clarify from here on out, I'm going to assume that the signal is phosphine, and the concentration constrained by the observations is 20 parts per billion. If you want to challenge that, I think that that's also a useful thing to do, but that's better done in conversation with the observers, particularly with Jane, who will be giving a talk in a few weeks. So first, let's just talk about the atmosphere of Venus itself. The atmosphere, as I said, is very hot. It's over 700 kelvins at the surface. It gets quite cool around 1 bar, and especially less than 1 bar. It gets below the freezing point of water. Water should condense out if there's enough of it. It turns out on Venus there's not really enough of it to condense out, but we'll get into that. What's more important, even than the temperature, except near the surface, is this particular strange coefficient that atmospheric chemists use called the eddy diffusion coefficient, which is a way of folding in a multitude of sins. It's a way of talking about turbulence and convective motion and any other sort of motion that vertically mixes the molecular constituents in the atmosphere. And the important thing here is that, at least with our best constraints, Venus's atmosphere near the surface is like molasses. It moves very, very slowly. It's a couple of orders of magnitude less efficient vertical mixing than on Earth. And so in principle, you can actually preserve molecules that wouldn't survive so well in a certain region of Earth's atmosphere, just because the diffusion happens to be a lot slower. And here are some of the observations made by variety of methods. All of these happen to be remote observations, but these can be compared to observations from Vega. As we can see, there's a fair amount of CO. The atmosphere itself is made up of primarily CO2. It's 99% CO2, or it's 97% CO2 with about 3% N2. And then the next most abundant thing is SO2, and that's what I'm going to draw your attention to. You'll notice that it at about 35 kilometers, it's about 150 parts per million. And then in the upper atmosphere, it gets down to parts per billion quantities. And that particular series of observations is what's driven a lot of the initial investigations into the photochemistry. And so we can look at Venus's atmosphere like this and look at the photochemistry that might explain, where is this SO2 going? It's relatively photochemically stable. Even if it isn't photochemically stable high up in the atmosphere, it tends to reform from its constituents. What's happening to it? So from volcanic production, you would expect some volcanic production of CO2, SO2, and water from the surface. Surface processes can end up giving you some of these as well. So even though I call this volcanism in my key, there may be other surface geochemistry that's going on that's not technically volcanism. The CO2 diffuses up, and when it gets high enough, it photodissociates into CO and oxygen. SO2 diffuses up, and it breaks up into SO and oxygen. And SO2 itself will react with the oxygen to form SO3. The water diffuses up, and the water will react with SO3 to form sulfuric acid, which then condenses out. And this is the main explanation for what happens to the sulfur dioxide. It's the explanation for why the sulfur dioxide depletes. And if this explanation is correct, then you can expect that the clouds of Venus are made up of about 90% sulfuric acid. Vega did measure some sulfuric acid while traveling through the clouds. Some people take that as some confirming evidence, although it's loose confirming evidence that that is what the clouds are primarily made of. Now, Venus's atmosphere is not quite this simple. There's lots of other things happening. There's more reduced sulfur species. And then there's a fair amount of hydrochloric acid in the atmosphere. This OCS diffuses up, and then it breaks apart into CO and sulfur, which contributes to sulfur allotropes. Near the surface, it breaks up to S and CO, and the S will also go on to form sulfur allotropes. The sulfur allotrope chemistry is quite complex. In addition, sulfur will react with HCl to eventually form hydrogen sulfide. In addition, there's a whole bunch of reactions that must be happening on the surface, and there must be a bunch of interesting surface geochemistry that maintains this, because a lot of these species are not long-term stable, at least not stable over geologic time periods. Oh yes, H2S itself also breaks apart and contributes to the sulfur allotropes. And HCl also goes up, and the chlorine does interesting things with the upper atmospheric chemistry involving oxygen chemistry. One of the important components in this is geochemistry. We are revisiting this from a volcanic degassing perspective in a paper in preparation led by Teresa Constantinou. And then, of course, there's also phosphine, and we don't know where that actually connects with all of these different explanations. So the atmospheric chemistry model that was used to try to describe all of this chemistry and see if it can reproduce the sort of observations uses the Argo-Lagrangian model, which I developed with Christian Helling in 2016. It uses a pastiche of chemical networks, which is referenced on the right, with some questions about the entire self-consistency and how the reversal of these reactions were taken. But this is one of the first full atmospheric models for Venus's atmosphere, and it's the first one to try to consider water self-consistently. We'll see what happened with that first attempt to consider water self-consistently. It has over 6,000 reactions, over 500 species, and it considers HCNO, S, and Cl chemistry with a handful of reactions for P, actually just for phosphine destruction. All it keeps track of is the phosphine destruction. And this is how it does for Venus's atmosphere compared to the observations. It does decently well for most of the atmospheric constituents. The SO2 is pretty much prescribed. You're welcome to ask me later why that has to be, but there are particular reasons why that ended up having to be prescribed. And the water, which we attempted to deal with self-consistently, it turns out ends up getting depleted and then photochemically destroyed in the upper atmosphere, but observations say that that can't be happening. Besides that, though, it ends up reproducing all the major constituents that the model can consider given the network. So then the question is, given this model, we can actually figure out how phosphine is destroyed. You saw that one of the lines on there was phosphine itself with an unknown cloud-based production rate. We can compare what's happening in different parts of the atmosphere to see how phosphine is destroyed. And one of the ways it can be destroyed is with thermochemistry. These particular numbers don't matter too much, except to point out that these are rate constants, so the units matter. This is centimeters cubed per second. And actually, yeah. And so what this is this is thermochemical destruction. So you take your phosphine and you just hit it with any other body. This will tend to happen more effectively near the surface of Venus. When a body hits, there's a chance that it knocks off one of those hydrogen atoms. And this is dependent on the density of the atmosphere. And so the more of those bodies that you have, the more rapidly it will go up until you reach a certain saturation. And the way in which this is balanced is using this Lindemann equation. So you have K infinity, and K infty is the same as K infinity. And Cardellino et al. Gave quantum chemical estimates for K infinity and for K at a particular pressure. But that left a degeneracy as to how to solve for K naught, which is the low pressure constant. It's the constant when the density of the second body actually matters. We found that there were two ways to figure out what K naught was. And those are given as K naught A and K naught B. Or what we could do is we could take K naught for ammonia and just say that phosphines like ammonia. And use that particular constant. We used all three of these, and then what we did was we just took whenever any of these constants is the lowest in order to give the longest lifetime possible for the phosphine in the atmosphere in order to give the best chance for competing explanations. The thing to emphasize with all of these is that the temperature barrier is on the order of tens of thousands of Kelvin, and this is the reason why it does happen slowly, but with substantial effect near the surface, and then pretty much above the surface does not happen at all. At the top of the atmosphere, phosphine can be broken apart by a UV photon coming in, knocking off one of the hydrogens. You're left with PH2. It's unlikely to find that particular hydrogen again. It'll react with oxygen or something else. Phosphine will be destroyed. And this gives the cross-section. The cross-section is a way of measuring the probability that a photon at a particular wavelength will do this particular reaction. And cross-sections of 10 to the minus 17 are very, very efficient given the number of photons that the sun is producing in those particular wavelengths. And so this is very, very rapid at destroying your phosphine, but only above the cloud tops. Within the clouds, it turns out that there's there's a lot of things which will absorb UV, but there's also this mysterious UV absorber, something we don't know what it's made of in the clouds, that's blocking a lot of the UV for deeper into the atmosphere. And this also blocks the UV that would be needed to destroy the phosphine. There's also other photochemical reactions. It can react with hydrogen atoms, oxygen atoms, chlorine atoms, or hydroxyl radicals. The important thing to notice here is that the barriers, either there are no barriers or the barriers are very small, and that these rates are actually quite large. These are pretty typical rates for reasonably rapid reactions with atoms or with radicals. The important thing, though, is that you need to know the concentrations of these particular radicals in the atmosphere. The concentrations are usually on the order of 1,000 molecules per cubic centimeter. And it's between that and maybe 1 molecule per cubic centimeter, or maybe 10,000 molecules per cubic centimeter. And every model gets very, very different answers for these. So we did not consider these destruction routes explicitly when we give the necessary flux to explain the amount of phosphine, just because we wanted a model independent sort of lower limit for the flux. But we can see in the figure what the particular effect is. Finally, phosphine, it's not actually destroyed by diffusion, but diffusion limits its lifetime in the sense that even though there are certain regions in the atmosphere where phosphine can live longer than 1,000 years, that would only be true if it just stayed there. And atmospheric gas doesn't just stay in one place. Even in the molasses-like atmosphere of Venus, it is moved around. The time scale for that is given by the height that it needs to move in order to be destroyed from the surface, divided by the eddy diffusion constant. And so that's what gives us this lifetime. This is a figure from Greaves et al. We'll ignore the formation right now. I'll return to that at the very, very end, but we'll just concentrate on the blue line, which is the destruction. The solid blue line is what we actually get from the model, and that includes the radical chemistry, and that's what creates these little bumps. So you'll notice that in the very upper atmosphere, the rate shoots up, the number becomes larger and larger, and so the inverse, which is the lifetime, becomes shorter and shorter. And that's because there's a bunch of oxygen atoms especially, but there's also chlorine atoms and various other things which just very rapidly destroy your phosphine. If you look below 40 kilometers, this is where a lot of the chemistry that happens from the sulfuric acid as it's settling down, it ends up going back into the gas phase. It vaporizes and then it dissociates. And the reactions with the water that is introduced and with various other constituents end up increasing the number of radicals in that particular region of the atmosphere. And so that shortens the lifetime as well. The dotted line is the more conservative lifetime that we get if we just ignore all of the radicals and just look at photochemical destruction at the top and thermochemical destruction from the bottom, and then diffusion in the middle. And when you do that, and we use the most conservative estimate, which is actually that we assume that phosphine is indefinitely stable and that it takes the diffusion time to reach 65 kilometers, whereas lifetime is much, much less than a year. And this would imply a flux of about 1 million molecules of phosphine per centimeter squared per second. And this is the bargain basement flux. You can't get much lower than this. And in fact, unless we're very wrong about the physics of Venus's atmosphere, you can't get any lower than this. The photochemical model requires a flux that's at least 10 times higher. It's probably much higher than that. I'll talk about that in future work where we try to better constrain this particular required flux. So we can start looking at some explanations. One explanation which is considered is volcanism. Maybe the phosphine is volcanically produced. There are some reasons to consider from Venera mission that the mineralogy of Venus, it's not very well constrained at all, but the mineralogy fits in somewhere around FMQ, which is around where Earth's mineralogy is. And then also just looking at interior evolution, there would be reasons to think that Venus is probably fairly oxidizing. And then if you look at the atmospheric components that have to be generated, especially the SO2 from volcanic degassing, that also suggests certain constraints on the mantle redox. Maybe you might imagine that it's as reduced as iron wustite, or maybe a couple decades below iron wustite. It would actually have to be about 10 orders of magnitude less oxygen fugacity than iron wustite, less available oxygen to oxidize the chemistry in order to switch over from degassing PO4 versus phosphine. So you could say, well, maybe not from the volcano itself, but maybe from the thermochemistry. So maybe something happens with a high temperature chemistry that breaks apart the phosphorus and ends up forming phosphine. William Baines and others, I'm also a co-author on this paper. This is a 100-page paper under consideration with astrobiology that tried to consider all of the ways that we could find a forming phosphine in the literature. We considered volcanism. We also considered thermochemistry. And for this, William Baines ran tens of thousands of different thermochemical models using different assumptions for uncertain barriers, uncertain Gibbs free energies for particular species. And what he gets, and the dotted lines show the constraints, is what the dominant species are. You tend closer to the surface, just as was mentioned before, to have a lot of P4O6. And then higher up in the atmosphere, you have a lot of phosphoric acid. You don't get a lot of phosphorus acid. You don't get a lot of other sorts of species, and you get negligible amounts of phosphine. But maybe photochemistry could do it. So photochemistry doesn't have the same constrictions as thermochemistry. This is the photochemical hypothetical network that William Baines has generated, given the best information that we have. If there's information for the phosphorus-bearing species, it's a solid line. If there's no information for the phosphorus-bearing species, it's a dashed line. And the dashed lines, for the dashed lines, we used nitrogen as a proxy. This is probably not an excellent proxy, but there are some reasons, given the sort of energetics of the analog molecules, to expect that at least the barriers might be similar. And so we ended up following through, and it turns out that if you start with your phosphoric acid, pretty much no matter what direction you go on this particular plot, you're going to go through this dark red region. And when we returned to the plot that showed the blue line, it also showed a red line. The red line is with the most favorable assumptions for all of these reactions for the production of phosphine. And the real reason why this struggles is not just because there are barriers, but also just because hydrogen is so incredibly limited in Venus's atmosphere. So there's also the possibility for exogenous delivery. In this case, we just considered the delivery via space dust and micrometeorites. Some of those micrometeorites will have some Schreiber site. What we did was we estimated the amount of phosphorus that would be contained in these micrometeorites. And we said that all of the phosphorus is contained in there is converted into phosphine. It's probably not true, but that's the most favorable assumption. And that the phosphine is all deposited into the cloud layer where the phosphine is seen. And we have this equation which then gives you the mixing ratio of phosphine, which is Avogadro's number multiplied by this mass delivery rate of phosphine times the longest time scale that we have in our model for the phosphine, which is the diffusion limited time scale, divided by the mean molar mass, or sorry, not the mean molar mass, but the molar mass of the phosphine, multiplied by the number density of the atmosphere, and then that is multiplied by that height where this is being deposited, and then by 4 pi times the radius of Venus squared. And when you do this, you end up with a mixing ratio of about 6 times 10 to the minus 13, which again is several orders of magnitude lower than the 2 times 10 to the minus 8 that you need to explain the observations. And this is not considering all the things that we considered, and then there are a lot of things that we haven't considered, but this at least gives you an idea about the things that you need to aim for in order to explain this observation. So I'm now going to go into a more speculative direction and say, well, what if it is life? What sort of things would that life have to be able to do? This is a reaction network that William Baines and Janusz Batowski especially have been working on to explain how phosphine might be able to be generated biochemically. No one really knows the mechanism on Earth. In fact, it hasn't been even entirely constrained which organisms are producing the phosphine in these anoxic environments. There's a lot of research that needs to be done, but the rate of production is known. And in typical anoxic environments, you expect a flux of about 10 to the 8th per centimeter squared per second. So if you had the clouds well populated with that kind of ecology, it would be more than enough to explain the amount of phosphine observed. In fact, it would be 10 to maybe even 100 times more than what you need. But we also need to remember that that's comparing to that bargain basement number. It may be that phosphine is more rapidly destroyed. And so these numbers may become closer to equal, or maybe we'll learn more about phosphine chemistry and find out that even life as an explanation is difficult to make work for phosphine. As we're going along on the speculation, how would the life in fact actually work? Not just how would it produce phosphine. You might also ask why it produces phosphine. You could ask that at the end of the talk and we could discuss that. But how would life even be there? Here's a brief history of, quote, life on Venus. I do think that it's more plausible that there was once life on Venus for various reasons, again, that you can ask me. It's a bit, though, controversial about what Venus's history was really like. There are two models that I'm going to discuss right now, one of which is that very early on within its first billion years, Venus was just a little too close to the sun. As the sun became a bit brighter, Venus went through a runaway greenhouse and turned into the hellscape that we all know and love, and has been that for billions of years. Another model, which has been proposed by Michael Way, first, I think in 2016, he's written some recent papers looking at various GCM models of what Venus was like, and he's able to run a history that's consistent with what appears to be a recent resurfacing of Venus. And the explanation here is that Venus was resurfaced maybe as recently as 600 million years ago. So a possibility is that Venus actually looked very much like Earth until as recent as 600 million years ago, when this resurfacing event happened, releasing a bunch of SO2 and CO2 into the atmosphere, boiling away the oceans, causing this runaway greenhouse and desiccating the atmosphere of Venus. And if you look at that particular scenario, you can imagine a case where you could have life on the surface. Some of that life might have gotten into the clouds. There's putative life in the clouds of Earth. I think there's pretty good evidence for that, but astrobiologists disagree. But if you can have an ecosystem in the clouds, you can imagine that as Venus heats up, and as this sort of habitable zone ends up moving up and becomes more and more acidic, the life might adapt for that lower pH. And so you can end up with a model that looks like this from Seeger et al. 2020, where you have these desiccated life forms near the bottom of the clouds. They get carried up. They're nucleating sites for the sulfuric acid. The sulfuric acid surrounds them. These little droplets run into each other and join together. The organisms rehydrate themselves somehow and then end up contributing to an ecology. They generate the phosphine and then they settle down, they desiccate again, and some of them inevitably drop out and onto the inhospitable surface. So this is possible. This is fairly imaginative. It's good to imagine as scientists, but it's also good to stretch the imagination to the point of also challenging some of these ideas. These are my two problems with the idea of life on Venus. These are not definitive problems by any means. One of them comes from this paper from Nature, Ecology, and Evolution, Hyperdiverse Archaea Near Life's Limits on the Polyextreme Geothermal Dowel Area. When you look at this particular area in Ethiopia. This is a lake that gets to 0 pH, and there's some good evidence that there is in fact no life in some of these regions because the pH is just so low. So you can see these microbial mats going to a certain region as the pH goes from a balmy 2, I think, down to 0. And as it gets closer and closer to that, the mats drop off, and eventually you get to a region that these scientists claim at least is uninhabited. This is still orders of magnitude less acidic than the clouds of Venus. And so this makes me wonder about the Jeff Goldblum line, life finds a way. Maybe life can't always find a way. There's another problem which I find almost more severe, which is that it's not just the pH, but it's the water activity. So the ratio of water to H2SO4, if I was going to make the clouds of Venus, I would take, say, 1 liter of water and 10 liters of sulfuric acid and mix them. But the problem is that the water won't stay as water. The water activity is driven down because the sulfuric acid dissociates, producing all of these free protons to react. And so the water activity, as projected by both experiments and models, is lower than about 0.01. And Earth's life limit, at least according to what I was able to find from a brief literature search and also from Wikipedia, is about 0.6. If there is life, I think that it's probably life as we don't know it. It would be life that may not need water as its solvent, or at least doesn't need nearly as much water as the solvent. A lot of open questions. Again, this doesn't exclude anything. It just shows how strange the idea of life is in this sort of environment. This is even more speculation, let's say, but this is speculation that's valid whether or not there's life on Venus now. If there ever was life on Venus, maybe it originated on Venus and on Earth separately. Maybe it originated on Earth and hitched a ride on a rock after a particular impact and ended up on Venus, or maybe the other way around. It hitched a ride from Venus to Earth. And in fact, there's no way to really tell at present. We could all be Venusians for all that we know. This might have happened very, very early on. You can look at models by Milosh and others that suggest that the exchange rate was fairly substantial early on. The neat part is, if there really is life on Venus, this is something that someday we might actually be able to answer, as whether there was a second origins. But this is many steps along the way and along a very, very speculative path. So speaking of next steps, here at Cambridge, the next steps will be to use a consistent sulfur network. I mentioned the pastiche, and I did that to be a little bit critical. The work in Greaves et al., I think, is pretty good for getting that bargain basement phosphine lifetime. But ultimately, you actually want a self-consistent network. Richard Hobbs is working on one. He's going to be applying it to hot Jupiters, but this will be the same network that will be valid for the core of Venus's chemistry. I'll be using that network and supplementing it with some of the sulfur chlorine reactions needed for Venus to figure out what's going on with the sulfur cycle. And I'm also going to be looking at a little bit of the sulfur droplet chemistry itself to see what might be happening in there. We're going to try to constrain surface processes and volcanism on Venus. Teresa Constantino is doing this work holistically, looking at the known constituents of Venus's atmosphere and the ones that are thought to be produced volcanically, and seeing what their ratios and their lifetimes suggest about the mantle redox. William Baines is also going to be pursuing this, but with a more phosphine-focused approach, saying, let's say phosphine is produced volcanically, what would the atmosphere of Venus have to look like? We are going to be modeling the spectra of Venus-like exoplanets. It's an interesting question as to what you could see if you took Venus and put it around another star. Sean Jordan is leading up a paper about that. Beyond our own group, though, the main thing that the observers will need to do is confirm or refute the phosphine detection. I'll let Jane touch on that when she's talking. We also need to explore phosphine in a broader Venusian chemistry in the lab. We need to understand more about what sulfuric acid actually does, what the droplet chemistry is like, what the optical constants for sulfuric acid even are. I learned from Sarah Horst that that isn't even known yet. Lots of things need to be determined about this before we even think about going there to look for something, because we don't know where to look or how likely it is that we are to be successful until we work out a lot more in the lab and with remote observations. And then once we do know, and even if we don't exactly know, eventually we should send a balloon or lander to Venus. It's an interesting question anyway to figure out what the history of Venus was. And it's also an interesting question to figure out, there's a lot of interesting chemical mysteries in Venus's atmosphere that it would be very nice to work out with a balloon experiment. I'm now going to finish with a little bit of a broader philosophical point about what these future possibilities may entail. I think every single one of them is exciting, and so that's one of the reasons I'm very, very excited about the future research. So one possibility is the signal is due to phosphine, or the signal is not due to phosphine. And then there's life on Venus, or there's no life on Venus. And if there's life on Venus, the life produces the phosphine, or the life doesn't produce the phosphine. And these options don't really entail each other, at least as much as you might think. So here's the most optimistic one in terms of our paper being right, although our paper doesn't really claim this, but some of the implications, at least the media took from our paper being right, you could imagine that the signal is due to phosphine, there's life on Venus, and the life produces the phosphine. Another possibility definitely is that the signal is due to phosphine and there's no life on Venus. Something else is producing the phosphine. But that's not the only option, because if there is life, then all the other options become available. So you could have something like this. The signal is not due to phosphine. There's still life on Venus, and the life is producing phosphine. It just doesn't produce enough for us to see. There's some abiotic process that works faster. Or this one is my favorite possibility, which I like to refer to as Gettier life. You can ask me why. The reason I call that Gettier life, but the basic sort of thing is that we believe that there's life on Venus, maybe because of the phosphine and other future measurements. It turns out we were right, but we were right for completely the wrong reasons. And this one in particular, I think, but all of these have some real implications for, oops, oh, we have to go through this again. All right, well, oh, but not all of it. Okay. Whatever the outcome, this result's important for biosignature detection on exoplanets, especially that last one, because then it really raises the question of what we're actually discovering when we find biosignatures. Maybe we're right and there's life on these planets, but we're completely wrong about the reasons for it because we didn't understand the proper geochemical context. And this also shows some of the challenges for biosignatures on exoplanets. Here's a place we can go to. And there's already a lot of argument about a putative biosignature detection for something that we can really see and resolve. I think that these arguments are going to get a lot more interesting as we start looking on objects that we can't explore at high resolution. And it's also one of the reasons why planetary science in our own solar system is so important, because here's where we can do the high resolution stuff to test a lot of these ideas that we will someday be applying to exoplanets. So with that, I will thank you. This is a picture of the entire team. I will highlight, it was Clara Souza Silva who first predicted phosphine as a biosignature on other planets, and Jane who first found phosphine on another planet. So with that, I'll thank you very much for your time, and I'll be happy to take questions.
Thanks so much, Paul. That was super interesting. Yeah, so if people want to ask questions, you could either drop them in the chat or just jump onto video and turn on your mic and ask the question, whatever you want. Whilst people are having a think about their questions, I wanted to ask a question straight away, Paul, about something you mentioned about Earth and there being some controversy over whether or not there's life in Earth's clouds. I wondered whether you could expand that point a little more.
So a lot of this, I'm not a biologist, so there's little that I can say except what I've read a bit in the literature and conversations that I've had. People like Lynn Rothschild are skeptical about there being life in the clouds, largely because a lot of the measurements apparently have been made by standing on mountaintops that impinge on the clouds, looking at those clouds and seeing that there is life in the droplets. There's a lot of questions as to how that life might have been contaminated from something that's about a meter away. So I do believe that there are still some controversies. From what I've seen and from astrobiologists that I know and that I've talked with, there have been other measurements that aren't quite as biased as that particular measurement, that also, some of them at least, indicate that there is an ecology in the droplets of Earth's clouds. But I can't comment any further. I just listen to people argue. I don't quite understand the terms and the reasons, and then I go on with my life.
Cool. I think it's fascinating there's a control even over cloud-based life in Earth's atmosphere, let alone the storm that you and your collaborators have begun about life in Venus's atmosphere.
Just real quick, this is something else. The Seeger et al. Paper touches on that controversy as well and talks about putative cloud-based ecologies on Earth today. So you can read about that controversy too in Sarah Seeger's paper. So.
Cool.
Yeah.
There's a question in chat from Rich Harrison. Has anyone been able to reproduce the anaerobic production of phosphine by bacteria in the lab, or is this only known from nature? By which I guess we mean just from the observation of phosphine.
Yeah. So Glindemann has done a lot of laboratory work, and it is reproduced in the lab. And actually, Sarah Seeger has another interesting paper which has nothing to do with this, but this is about life in hydrogen-dominated environments, where she and her group were able to grow microbes in H2-dominated environments, and then they saw what sort of biosignatures these microbes produced, and phosphine was one of them.
But did you suggest that the mechanism or the motivation for the phosphine production by life remained a question, even if its production was not necessarily questioned?
So I can imagine an easy motivation for phosphine production on hydrogen-rich planets. You have tons of hydrogen to work with. You have a lot of free energy. It's a great waste product. On Venus, which is really oxidized, it's really hard for me to imagine that you're just going to degas all of this valuable hydrogen when you could be using it for more useful things. But that's again, just speculation. Life does a lot of sort of Sisyphus-like tasks in their metabolism. Maybe this is one of them, but it still seems a very strange one if you're lacking a resource to just sacrifice it like that.
A question from Elliot Lynch from chat. How sensitive are the results to the details of the atmospheric dynamics, and are these well constrained for Venus?
So the atmospheric dynamics are not especially well constrained. A really nice paper about this is the full photochemical model paper, the first one, if you count ours as second, by Bierson and Zhang. And this one actually shows that you can play quite a bit with the eddy diffusion coefficient in order to better explain the sulfur depletion. There are various other ways in which this might be able to be constrained. Ideally, other probes that were really carefully measuring these sorts of things are better. There are some early measurements, but it's hard to just take one probe, take that single measurement and say, this represents all of Venus for all time. And so there are a lot of uncertainties. The sensitivity to those uncertainties is substantial in the sense of if Venus is much more dynamic, then the lifetime goes down. It becomes much, much shorter. Even if Venus is much more stagnant, you're still left with certain radical processes and other things that will eventually destroy your phosphine on the order of, instead of hundreds of years, there might be small regions where it might be able to last for thousands of years. But then the real problem is, let's say that it's slow. Well, then how do you get it to the cloud so that you can see it? You're very slowly moving it through regions where its lifetime becomes shorter and shorter and shorter. And so I think that you'll run into different problems. I think that the stuff below about 50 kilometers might change quite considerably, but I think the stuff above that would still not change so much, even if we're wrong about the dynamics.
Craig Walton's asked about the H2SO4 in the clouds, and how wrong could we be about the clouds being H2SO4?
So potentially quite wrong, because again, we don't have a direct observation, and you should have direct observations of these sorts of things, ideally, before making very strong conclusions. One of the things that you could say is that either there's something that's really missing in our understanding of the clouds of Venus, or the clouds are as acidic as people project, because you have to have some way to remove the sulfur dioxide. And when you do that, you form a lot of sulfuric acid.
Cool. Yeah, I mean, it's interesting how that's then embedded in one of the many puzzles that Venus has presented over the years. Richard Hill's asking, is the assumption of only 1D valid? Asking about day-night, equator pole. So I guess that's kind of a spatial, temporal kind of dimensionality to the problem. And does that open up any parameter space for phosphine production that the 1D model doesn't access?
I sort of asked that as you were answering the question about dynamics, so you'd partly answered that already. But I was partly also thinking of the fact that the ALMA observations must give you lots of independent resolution points. And I was a little bit surprised that the paper didn't make more of that. It seems to me you should be able to see whether you're seeing it uniformly over the disk or different on different parts of it.
Yeah. So the paper does discuss it very briefly. ALMA does get a map, and you have these regions between the equator and the poles where the phosphine is most observed. You don't see it near the poles, and you don't see it at the equator. And so there is a latitudinal distribution. And in fact, I should have made a good backup slide about this. There's a nice figure, figure in the extended figures in the paper, which shows what you can do with the timescale with this kind of with these latitudinal winds or with the zonal winds in terms of the lifetime. Because what you would need to do is, if you had your production, say, in one region of the atmosphere, how well mixed would you expect your phosphine to be over the surface? And you can calculate that. And it turns out the latitudinal winds are probably very slow. The zonal winds are insanely fast. If you saw a zonal variation, then that would suggest that the phosphine was high enough that the production rate would just have to be just mad. It would just have to be super, super fast in order to exist at the height where you'd be able to see variation in the direction of the zonal winds. But latitudinal variation would be expected because the winds there are slow enough that if it's in the higher regions, so say around 65 kilometers, you would actually expect to see a fair amount of variation around there. If it's deeper than that, then you would expect it to be uniform throughout. But
again, I probably should have read the paper more carefully, and maybe these are questions for Jane, but I mean, from the shape of the profile of the line, you can tell what altitude it's at because the width of the line gives you the pressure. So I assumed that was fairly well constrained, at least the phosphine you're observing.
So I will give a very brief comment about that, and I'm going to try not to get myself into too much trouble. That is more of a question for Jane. The way in which the data was reduced, because Venus is so incredibly bright, and the way in which the data is produced, the wings of the line are not especially well preserved. And so it's difficult to make strong assumptions about exactly where the phosphine is. The strongest constraint that I think Hideo Sagawa was able to make was, is pretty well known where the continuum is. And that's at around 60 kilometers. So it can't be much deeper than 60 kilometers or you just wouldn't see it. There may be phosphine below that, but it doesn't contribute to the absorption.
Sure. I mean, the way you see the line at all is there has to be the molecules in a colder column that's above wherever the continuum's coming from. And so with the temperature going down, that's possible. Okay. As you say, probably should wait for Jane for
definitely
details on those sides. Perhaps I could just say finally, you just mentioned the complications about processing, and I certainly would like to understand those better. And I was rather shocked to see that John Carpenter, who is, I think, chief scientist at ALMA, went on the record to say that he thought that this could all be a figment of the processing.
Yeah, that I think was actually in the National Geographic article. And again, I'm not competent to comment on that. The only thing that I would say is he also said that all the protocols were followed. I think that the real way, at least for myself, to really convince me that this is both really real and really phosphine would be to see something beyond just the single line.
Oh,
it's
sure.
Risky to make very strong conclusions off of
Absolutely. It's just unfortunate that I don't think there's another line that's in any of the bands that are easily accessible from the ground. Isn't that right?
Yeah. That would be the short answer. There's a more interesting long answer, which I'll leave for Jane to give.
Yeah.
So that you can hear it correctly.
Thanks, Paul. I know we've gone on beyond 3 now. Are you happy to keep answering questions whilst there are questions?
I can answer a few more questions.
Cool. Matt's asked, do we have any idea how life would propagate on Venus? Is it expected to look similar to life on Earth? I guess maybe you'll touch on that a little bit. And do we have any idea what the DNA chemistry would look like at the pH expected?
So if it was exposed to the sulfuric acid, there is no DNA chemistry. Because part of what builds DNA is also the sugars, and there's a wonderful experiment that you can watch William Baines do. You can watch lots of people do it, where they pour sulfuric acid on sugar. And that's kind of what you would expect to happen to DNA. You don't have the oxygen contributing, so it won't be quite as violent, but it'll still be an incredibly rapid destructive reaction. The way that you would need to protect from that is to have something like plant cell walls that keep a relatively neutral pH on the inside, and then allow for this very acidic pH on the outside. One of the challenges is that for something as acidic as Venus's cloud droplets, it would need to be made of something like Teflon. And then there's the open question of how do you get stuff in and out? Because you need to get stuff in and out. Cells produce waste and they want to eat. And how do you eat and how do you discard your waste if you're surrounded in Teflon? So because of these challenges, it's hard to imagine life as we know it working there. It may be that completely different chemical solutions were touched upon that allow this to work with a somewhat more acidic environment in the cell, but it can't be that acidic, I don't think, at least not for any sort of life that I can imagine.
Well, I think you missed an opportunity to title the paper "Teflon-Based Life Discovered on Venus." Let's write that. Try and get it on the archive by tomorrow. Andrew Tenetzups asked, thanks, Paul, for the talk. Can the isotopic composition of PH3 be measured? And if so, do you think it would differ between microbial versus abiotic sources?
Great question. I have no idea.
Yeah. I guess that would be trying to get the HD ratio. Interesting question. Claire Gimmon's asked, will there be a point where you've ruled out enough abiotic sources of phosphine that you can say it is life?
No.
I guess that's kind of asking, what's the threshold for belief in, I guess, a general statement.
My sort of attitude is a kind of Bayesian one. If you want to personally believe that there's life on Venus now, that's fine. And if you want to personally believe that this evidence doesn't change things very much, that's also fine. These are prior probabilities. And then there's the evidence. And if you have a reasonable prior and you have good evidence, the evidence always overwhelms the prior. And so the posterior probability is informed by the evidence and not by the prior, which represents your biases, your emotions, your beliefs, whatever else. Right now, people with very reasonable, very different biases come to very different conclusions after looking at the evidence, which suggests to me that this is not sufficient evidence. And it won't be until there's quite a bit more to really say that this is sufficient evidence. I think that the chances go up as more and more abiotic processes are really looked at. We've just started the story. Almost nothing has been looked at what phosphorus chemistry does in sulfuric acid droplets, for example, which would seem to be a logical thing to look at. And so once that's done, if it just turns out that you don't end up producing it, or you just end up destroying it incredibly rapidly, You can enhance the mystery. And the mystery doesn't always need to favor the probability that there's life. You might end up finding out that all known abiotic processes aren't nearly fast enough because now the timescale's gotten much shorter. Now that you've looked at the droplet chemistry, the timescale's gotten even shorter. If it gets too short, then it's hard to explain how microbes, as we know them, could possibly produce enough phosphine. And then it becomes, again, more likely, at least in my mind, that it's some incredibly productive unknown abiotic source rather than a biotic source that's more productive than any that we know. And so the answer is that it can go both ways, but ideally it should be informed by the evidence. And for myself, I don't think the evidence would ever be sufficient for me to claim confidently this life until someone sent a probe there, got a sample, brought it back. There was very little chance of contamination. They grow this cell culture in the sulfuric acid droplet environment. Then I definitely believe it.
Yeah, on contamination, I'd been wondering whether or not the early probes to Venus could have contaminated the atmosphere.
Yeah, so that's a great question. The answer is that given the plausible rate of production and proliferation and the sort of dynamics of the atmosphere itself, and also the time for those microbes to evolve a way to deal with the incredibly hostile environment, all of those combinations make it exceedingly unlikely that a handful of microbes on one of these probes happened to give rise to a completely stable and productive ecosystem.
Cool. I think that's all the questions
Great.
I can see. Thanks so much, Paul, for giving us a talk on the topic so soon after the article being kind of off the press.
Sure.
And like Paul said, Jane will be speaking in a few weeks' time. So watch out for that announcement because that'll be a kind of interesting follow-up, especially in light of whatever else has come out in the interim to kind of add mystery and complexity to the story. So yeah, thank you, Paul. Super talk. And thanks everyone for joining.
And thank you very much for listening and for asking interesting questions. I hope to see a lot of you around, maybe even in person in the near future. I can dream.